welcome to the Astronomy Club of Akron's January meeting. Did everyone get a raffle ticket? Okay, we have
This will be interesting.
4 planispheres that we're going to raffle off. After the presentation, that's when we'll have the raffle, and then we're going to have our business meeting. So today we're going to have our telescope seminar, and we're going to have Phil Creed is going to be talking about refractors and eyepieces. John Crilly is going to be talking about reflectors and Schmidt-Cassegrain telescopes, catadioptrics, and I'm going to talk about binoculars.
All right.
Binoculars are great because you get a very binoculars, they give you about 6-degree field of view, so it's great for looking at comets, large open star clusters. I'll talk to you about a little bit about some things to look at. I have a book that I would recommend taking a look at. But what I want to do first is just give you an idea of how to operate the binoculars. So when we take a look at the binoculars, we see there's a few different moving parts. We have this hinge. Okay, we have a hinge, and then we have this barrel, which drives the eyepieces up and down. Okay, that's for focus. And then we have this knob over here, which rotates one of the eyepieces back and forth. This is called a diopter. So the way you want to set your binoculars up is take one of your lens caps and put it over the objective that has the diopter. That's the knob that turns. Okay, so put it over. I'm sorry?
Oh.
Okay, put it over there.
Never thought to do that.
And then, so what we're going to do is we're just going to look with the left eye through this objective. And you want to look at something at infinity. If you're looking at stars, that's a great place to look. And you'll rotate the barrel, and that drives those eyepieces, and you'll just bring it into focus until you have a pinpoint of light. The star is just a pinpoint of light. So once you have a pinpoint of light, then just let it go. Don't touch the barrel anymore. Then what you want to do is take the cap off, put it on the other side. Now look at it with this eye. And the reason we're doing this is because your eyes aren't exactly the same, so they focus a little bit differently. So now we're gonna set this eye. We have this eye set, now we're gonna set this eye. So you put the lens cap over this side, now look at that star again. Don't touch the barrel, you want to adjust with the diopter, and you just bring it into its pinpoint of light. Then you have the binoculars set. Then you don't have to touch the diopter anymore, and you could, if you're focusing at something close, then you just rotate the barrel to get things in focus.
Can you do that, Daddy?
Yes.
Now, binoculars are good. You know, these are rated. These are 10 by 50. That means the 10 is the magnification, and the 50 is the diameter of the objective. So for astronomy, that's pretty good. 50s are pretty good. If the general rule for binoculars, if you're over 10, you need a tripod. If you have pretty steady hands, you're pretty good up to 10. Sometimes I find that even at 10, the image is shaking quite a bit. Now this does come with a 1/4-20 thread there. So you could mount this onto a tripod. It's just take an adapter like this, thread it in, and then you could just have that sit right on top of your tripod. You got another 1/4-20 thread there, and just thread that right onto the tripod. If you're anywhere over 10, you really need to have a tripod. So that's one of the things. Now I'll show you, this is a pair of, these are really astronomical binoculars. These are 9 by 63. So the magnification's down, so you don't have to worry so much about having the image shift around, but you have a very large objective, 63 millimeter.
Oh.
So it's going to bring in a lot of light. So these are also what's called multi-coated. Actually, every surface is multi-coated. There's a special type of coating they put on, which is exactly about a 1/4 wavelength of light thick. So what it does is it stops stray light from getting into the instruments, so you don't get a distorted image. The coating is a quarter of a wavelength thick, so when light goes in, it goes a quarter, and bounces back out, it goes a quarter, and then it will exactly cancel another wave coming in, because it'll be a half wavelength out of phase. You'll have a crest and a trough match up, and it'll cancel out. So any internal light that's moving around, it'll get canceled out. So typically all surfaces for any astronomical device, whether it be binoculars or telescope, they're all multi-coated. Every surface is coated. So these are pretty cool. Now, when you get into higher magnification, or you just don't have steady hands, this is a nice set of binoculars to use. These are called image stabilization binoculars. So what happens in these, this is a Canon, these are 10 by 30s. And what happens in here, there's a sensor that will detect any type of motion. Okay, it's going to detect even, I mean, you may not think you're moving, but just your heartbeat is causing this thing to just a tiny little shift. And when you're magnifying by 10, all of that is amplified. So if you're looking at an image, that little shift, you may not think it's much, but it's moving that image around quite a bit. So the nice thing about these is it has electronics inside. There's a sensor, and it based on which way you're moving, it will adjust the prisms inside to keep that image stable.
Wow.
And you run it through the same calibration that we did with the other binoculars, but it has this button here, one extra button here, that you press. See the green light there? That means it's activated. So when you're looking at an object, just press that button and it will stabilize the image. And it works pretty good.
Cool.
The downside of these is they are expensive. And the larger diameter objective you get, the more you're going to spend for it. This is only 30 millimeter objective, so that's pretty small. Yet these are like probably $550 to get that electronics in there. So a little bit more, something like what we looked at here. These are probably $75, and this is a more expensive set. This is probably these are probably close to about $300 now. I think I paid maybe $270 for them, a couple of decades ago.
So you don't throw them in your
So,
right?
We've got a bunch of different ones. If you want to come up here and look later on, we have some binoculars. These are from the 1950s, Mann binoculars. You want to take a look at these. The nice thing about this, you look at the glass and it looks absolutely pristine. So all those years, and they're really good. If you go to the opera, got some opera glasses. Here's another type of thing you might want to use. This is a monocular. So you just get one. You want to take a look at this. This is pretty cool. It's actually like a little telescope because it has a mirror in back. There's a secondary mirror, and then there's going to be some type of prism in there that's going to flip the image around so you get, upright and left, right is correct. So you have the correct image. But these are 10, magnification 10. And I find it to be a little bit hard to hold. I can't quite, it's really hard to keep it stable. It seems to be moving around a little bit on the image. That's just me. If someone has steadier hands, they would be better. But you could also just brace this against something and it's not going to move. You'll get a steadier image.
They have night vision too.
Yeah,
Okay, so this is a book I would recommend. It's not in print anymore. They do have a second edition. This has 99 celestial objects to look at with binoculars. There's a new one. I think it has 119 or something. But this is, Sky and Telescope put this out a while ago. This is decades ago. But you could still get the second edition. And what it has is a whole list of all different types of binocular objects. Like I said, 99 in this book. It comes with a map of the seasons, and then you have the different objects that you would be searching for, and then it gives you a one-page description of what that object is.
That'd be nice, huh?
So it shows you, for example, here's Kemble's Cascade. So it shows you the field of view of the binocular, which is going to be roughly around 6 degrees, and it gives you a description, and in this case it's also, you're also bringing in NGC 1502, so you get the nice description. pretty nice book. I would recommend this. So there's a lot, you might find it in the library, you might find it online. I wouldn't spend any more. Sometimes if you're looking on Amazon or something, those prices are absolutely crazy. I've seen the second edition on this go for $194, but you know, the price is, for new, it's $24.95. I got this one for $20. But I wouldn't pay anything more than that. You can probably get it at the library or check back because they have deals. You know, you'll see it on Amazon, it might be, you know, $50, $60, and then you go back a couple weeks later and someone else is selling it. Maybe a library's selling it, they're getting rid of it, and you get a good deal, $20 or something.
I actually just found it on Amazon for $30.
30. Yeah, 30 is a little high, but that's, definitely won't go any more than that.
I have a question. Where's a good place to buy binoculars? Do they still have cames? Do they still have cames?
I think it's closed.
Is it closed? I used to go to cames for stuff like that, but I don't know where would you go to get a pair of binoculars?
I do, most of my stuff is online.
Okay,
Woodland telescopes.
Okay.
Yeah.
You know, like Walmart or something wouldn't probably have anything, or?
You wouldn't find anything like this in Walmart.
Okay.
The only way you're gonna buy this is online. You could you can get these on Amazon, you'll have distributors that will be advertising on Amazon. Walmart, I'm not saying their stuff is inferior or anything, but it's not astronomical grade.
Dollar General?
Yeah, not Dollar General.
I would look at,
The plastic one?
That's where I go.
Yeah.
right, yeah, I would look at Cabela's, some
Oh,
of
yeah,
the hunting
okay.
stores.
I would think some of those
Dick's.
places.
Oh,
or
yeah,
that
that's a good idea.
Buck,
Dick's has some of
with
that stuff too,
fur
but
and
Thought
not.
about
Ben
that.
and-
Hunting stores, that's a good
Feather
idea.
fur.
Yeah, a lot of this stuff
I'm
is
not
like,
an
if
online
you're using
shopper.
them for birding or something,
Yeah,
you'll find it in those locations.
I actually bought a couple good telescopes from Best Buy. You wouldn't expect it, but they were
Oh, that's
decent.
nice.
Little ones.
Yeah, Best Buy. Woo.
Sounds good. Okay, we're gonna move on to Phil Creed. He's gonna talk to us about refractors and eyepieces.
Okay, hi there. I was going to talk a little bit about refractors and eyepieces. If you're looking at when you think of a telescope, the mental image that most people think of when they think of a telescope is a refractor. You have a lens, it gathers light, brings it towards the focus, and then into your eyes. This refractor right here, I'm going to reorient it so it matches what you see right there on the diagram. This is the objective lens. This is what's going to gather the light, and it's going to form a cone of light that's going to converge and out the prism there, so you have a comfortable viewing angle. And all a telescope does is it just simply gathers a lot of light and brings it into your eye. The binoculars, if you want to think of it in a way, binoculars are essentially two refractors with a folded light path for convenient observation and very portable. Pros and cons of the design of a refractor: they are top-notch in terms of image quality because there is no obstructions whatsoever in the light path. Aesthetics, it just looks like a refined telescopic instrument. You can see like the two refractors behind you right there. I mean, those would look great. That would be something you could probably put in your living room. It just looks, people just intuitively see that as a refined instrument. Because of the fact that the big lens is going to be on the top and the diagonal, which is where you're going to put your eyepiece, is on the bottom, this allows for seated observing. Observing with refractors can be quite comfortable. They're great for wide field observation. They are the simplest operation. You do not have to do any kind of aligning of optical components, what's known as collimation, and John Crilly will get into that a little later on. If you're starting out with astrophotography, this is definitely the thing you want to use, because I have done astrophotography for the past 7-8 years. Astrophotography in and of itself is really hard. And using the simplest telescope design for that definitely helps. Now, do they have a disadvantage? The biggest one is they cost a lot. They are going to be the most expensive design per inch of aperture. And that's important because you're gathering light. Everything in astronomy is about gathering light. You're gathering light from, say, something that's this big into a pupil that's maybe a quarter of an inch wide.
Whoa.
So the more light that you gather, the more you see, okay? But a refractor, like once you get into 6-8 inch refractors, they become extremely expensive. The other thing is that your standard astronomical refractor, which uses a prism diagonal, it will give you an image that is right side up, but it's mirror reversed. So it's okay for terrestrial observation, but just beware of that. Now, if we really want to go back in the day, and by going back in the day, I mean about 400 years, this is Galileo's telescope. The first telescope used for detailed astronomical study. It had a whopping 1.5 inch of aperture. So, if you can imagine, it would be, the lenses would have been roughly about the width of those lenses. And it didn't have a huge amount of power. I think it was maybe 20 or 30 power on it. But you gotta remember, everything up to this point that was observed in the heavens was just with the naked eyes. So this opened up the cosmos to humanity, caused the light path to converge. The problem here is that not all wavelengths of light converge to the same point. The blues and the violets are going to converge to different points than the reds. So the result is that you will have all those wavelengths of light not coming to a focus. So you'll see like what looks like a colored aura around a bright star or a planet. And this is known as chromatic aberration or false color. Now, in the early times, they found a way to get around this thing. And just to go back real quick here, you're going to get a lot of chromatic aberration because this has a very short focal length. So one of the most preeminent observing sites in the eastern United States. And I had a fabulous time with it. It was just like a match made in heaven. There is something to be said for having the right tool for the job. Now, what was later developed were called apochromatic refractors. And astronomy author Phil Harrington had a great definition of it. He said, if achromatic means no color, apochromatic means no color, we really mean it this time. So these use what is known as ED glass, or extra low dispersion glass. And most of these are either doublets or triplets. And you can see the difference. This would be like what you would get with an achromatic refractor. You see that purple? Okay, that's chromatic aberration right there. Same star field, only shot with an apochromatic refractor. These things still are going to scale up quite a bit in heft when you go up in aperture, but this allows for much more manageable sizes. A 4-inch achromatic refractor that is color-free is going to be about this long. A 4-inch triplet that is apochromatic is now about this long. So it's much more manageable on a mount. It's much easier just to pop it in the backseat of the car and just drive somewhere. Now, if you're going to look through I probably should mention real quick here, if you're going to be doing astroimaging, you want to have an apochromatic refractor. You can use an achromat, but you're going to get a lot of this. And one thing I should point out, if you can see it with your eyes, it will show up a lot more in the camera because the sensors are much more sensitive than the human eye. Okay, so you got your telescope. Now you actually want to look at something with it. You need to have an eyepiece for visual observation. So you want to use an eyepiece. And in this particular telescope, that's what this little guy is right here. And well, I can't quite. Just yank it out. Okay. That's almost a press fit in there. So this is what you will need in order to observe visually. And with a refractor, you just pop it in the diagonal. With a reflector, I'm gonna set that there for now. With a reflector, it's going to be on the focuser that's on the side of the tube near the top. The selection of your eyepieces is very dependent on the target and the observer. I mean, do you like looking for big objects, or do you like looking for tiny little things? So eyepiece characteristics are things that you're going to classify eyepieces under. Barrel size. In that case, this little eyepiece right here, that looks like a .965 diameter. The most common ones nowadays are 1.25 and 2 inches. Focal length of the eyepiece, the amount of eye relief, the apparent field of view, and how well it corrects for aberrations. When I talk about characteristics of an eyepiece, do you notice there's one thing that I didn't put down there? Power. Magnification is not an inherent property of an eyepiece. And we'll get into that later as to why that is. Okay, as I mentioned, barrel sizes. Most of your telescopes nowadays will take 1.25 or a 2-inch barrel. I'll show you some examples. This right here, this is a Meade 5.5 millimeter. Has a barrel size that's 1.25 inches. And some eyepieces have a 2-inch barrel. This thing right here, which is a 31 millimeter Teleview Nagler, has a 2-inch barrel. Teleview was very kind to take the scorch marks off of it from whatever howitzer it's launched out of. This thing is pretty heavy. It weighs single-handedly 2 pounds. And then you have some eyepieces that have a dual barrel. This section right here is 1.25 inches. This section right here is 2 inches. So you can use it in either, if your focuser is configured for 1.25 or 2 inches. If you're doing a lot of low power wide field viewing, a 2-inch eyepiece is very nice, but it also, you know, this is where you also have to look at your telescope. Does your telescope have a 2-inch focuser on it? So, we mentioned power not being an inherent property of an eyepiece. If you ask, well, what power is the eyepiece? And that is, it depends on the telescope. The magnification is simply the focal length of the telescope divided by the focal length of the eyepiece. So if I've got, let's say I've got a telescope that has a 1,000 millimeter focal length, and I've got a 20 millimeter eyepiece. Well, 1,000 divided by 20 is 50 power. If I have that same 20 millimeter eyepiece, but I put it in, say, an 8-inch Schmidt Cassegrain, which has a focal length of 2,000 millimeters, 2,000 divided by 20 is now 100 power. So it's going to depend on the focal length of the eyepiece and the focal length of the telescope. And as a general rule of thumb, you want to avoid going more than 50 power per inch of aperture. So if you have a starting telescope that has, say, a 2-inch aperture, you don't want to put 500 power in it. For a 2-inch telescope, you probably wouldn't want to go beyond 100 power. Focal length selection. Now again, you're taking the focal length of the telescope divided by the focal length of the eyepiece. So, the higher the focal length of the eyepiece, the lower the power, and the opposite is true. So if you want to do a lot of big objects which require low power and wide field of views, you want to go 20 millimeters and up. You want to go 10 millimeters or less for things that are high power, and 10 to 20 is a nice little middle ground, at least for a lot of telescopes. But again, this depends on the system. The next thing you have to factor in is what's known as the exit pupil. If you pop a telescope into an eyepiece, let's do the opposite. Highly recommend do the opposite. If you put the eyepiece in the telescope, you're going to see a little cone of light This just looks like it's kind of floating there. That's known as the exit pupil. And the size of that exit pupil is relevant because that is the diameter of the light that's actually coming out of the telescope into your eye. How do you figure this out? Is you just simply take the focal ratio of your telescope and you factor in your eyepiece focal length. So if you've got a 24 millimeter eyepiece and you have an f6 telescope, 24 divided by 6 means you have a 4 millimeter exit pupil. The significance of the exit pupil is this: if your exit pupil is more than 7, you're wasting aperture because that circle of light that's coming out is actually wider than your dilated pupil. So you're basically wasting light. You can't see all the light that's coming out of the telescope. If it's very, very small, you get a very dark background, and it's a little complicated to explain, but basically, like when you get really small exit pupils, if you look at something bright, that's when you start noticing floaters in your image. Your overall best exit pupil is 2 to 3 millimeters, or a good rule of thumb is that your clutch eyepiece, the one that you're probably going to find the best balance of power and field of view, is about 10 power per inch of aperture. So if you have an 8-inch telescope, something that's going to give you about 80 power is probably going to be your go-to eyepiece for a lot of things. The other thing that is an important property is what's known as eye relief. How far back from the eye lens can you put your eye and actually see the image? If you're somebody like me who has to wear eyeglasses because I have astigmatism, you want to have a good amount of eye relief. They recommend having at least 15 millimeters of eye relief if you wear eyeglasses. If you don't need glasses, you can just take your glasses off and you can get closer to the eye lens and not have it be a problem. That being said, even if you don't require, it didn't occur to me I'd have to put that on and then the headset. Even if you don't require eyeglasses, if you're getting down to 5 millimeters or less of eye relief, it is very, very uncomfortable. It's a transcendental experience. Your eyeball will become one with the eyepiece, as I like to say. This is the reason why I don't use 4 millimeter ortho eyepieces and things like that. The other thing is what's known as apparent field of view. So when you look through an eyepiece, you're going to see like a circle of light, and then everything outside of it is dark. Well, if the angle from one end to the other is, say, 50 degrees, it's going to kind of look like this to your eyes. If it's 60 degrees, now it's going to look more like this. If it's 70, and then now as you're getting out toward 80, now it's looking more like this. You'll notice in all three of these pictures that the image scale is the same. So this would be like try to imagine you're using an eyepiece and all the magnifications, all the focal lengths are exactly the same. The only difference is the apparent field of view is bigger. Now that's nice because if you're using a telescope that doesn't have a drive, a bigger apparent field of view helps the object stay in there longer before you have to eventually nudge the telescope. But as you might suspect, the bigger that number gets, the bigger the amount of money required to get one of these. As far as eyepiece operations are concerned, most eyepieces are going to have a very nice image right in the middle of the field of view. Toward the edges, that is where things get more interesting. The most common aberration was known as off-axis astigmatism. And if you look toward the edge of your field of view, it kind of looks like seagulls. This is very prominent when you get fast systems. When you talk about F ratios, the ratio of the focal length divided by the aperture. If that number is low, like F6, F5, then this aberration shows up quite a bit more than if it's, say, F10 or longer. The better eyepieces will tame this pretty well to the point where you won't even see it, but they will cost a lot more money.
Phil, elementary question.
Yeah,
What's the relation of the F number to the focal length as a distance they use to calculate power?
the F number is simply the focal length of the system divided by the aperture of the system. So if I've got a telescope that's got 1,000 millimeter focal length and it's got a 200 millimeter objective or aperture, it's F5. Little mantra as far as eyepieces: good, cheap, wide field, pick any two. If it's a good eyepiece and it's a good wide field eyepiece, it is not going to be cheap. If it's a cheap wide field eyepiece, chances are you're going to see a lot of this toward the edges. Now, Barlow lenses, this is a neat little hack that you can use to greatly increase the number of magnifications at your disposal. What this does is it will increase the power of any eyepiece you put it in, typically by a factor of 2, but there are other ones, there are other factors. There are 2.5s, there are 3x's, there are even 5x of Barlows out there. And if you're looking to expand the amount of powers that you can use, but you really don't want to spend the money for like another eyepiece, these are great. So if you have a 2x Barlow, effectively what you're doing is you're doubling the magnification, or if you want to think of it another way, you're halving the focal length of your eyepiece. So if you have a 12 and an 8 millimeter eyepiece and then you throw in a 2x Barlow for 50 bucks, you now have the equivalent of a 6 millimeter and a 4 millimeter eyepiece on top of it. Not a bad investment for 50 bucks. Especially if you're 12 and you're 8, or say a 12 and an 8 millimeter Teleview Delos, which even used are going to run you $250 to $300 a piece. So having a Barlow lens is something that I would highly, highly recommend. And I want to wrap this up with just a brief summation on this. If you have a few good eyepieces, that's going to beat a collection of mediocre ones. 2 or 3 really good eyepieces plus a Barlow lens, that's a great package that you could easily spend all night with. You want to go for one that has a 2 to 3 millimeter exit pupil again, or about 10 power per inch of aperture. That's going to be your clutch performer. And I know this sounds like sacrilege to the Teleview crowd or the premium eyepiece crowd, but don't stockpile expensive 2-inch wide field eyepieces. Okay, and what I mean by that is it's nice to have one of these things, you don't need 4. When you're dealing with low power viewing, you know, that's great for the big objects. That's great for looking at the Orion Nebula or the Andromeda Galaxy. But most of the objects you're going to look at, like a globular cluster, think a planet, you know, they're going to be small. So you don't need to spend a lot of money on premium 2-inch wide fields. It's a good idea to have maybe one good 2-inch wide field. You just don't need a whole bunch of them. And that is it. And I think I'll hand it over to Ron for the next segment.
One more question.
Certainly.
What's the reason to not up the power? You said not go up the power with so much of a ratio of the aperture. What's the reason? What happened?
First of all, your aperture forms a limit to your resolution in terms of like your aperture is going to how do I explain this? If you have an 8-inch telescope, at 50 power per inch, you're at 400 power. Okay, you're not going to gain. You're not really going to see much more detail beyond that, no matter how steady the atmosphere is, unless you get really, you basically just get more aperture. The more aperture that the instrument has, the greater the resolution you would have. I guess the technical term would be that once you reach a certain magnification, the amount of detail you can see is diffraction limited. Yes?
You mentioned a place called Cherry Springs, I think.
Yes.
Is that an observatory open to the public?
No, it is a state park that is open to the public.
Where?
It has a general camping area. On one side of the road, on the other side is the observing field. And you have to pay a nightly fee, and I think it's like $25 now per night. But they're pretty restrictive in terms of like the kind of activities you have there. Like, you know, if you just happen to, if you want to cause a riot, do this.
We did once.
Now, this does, I mean, this is bright, yes, but you're thinking, well, this doesn't, I mean, this isn't terribly bright. When you're in a sky that dark, and everybody's eyes are fully dark adapted, okay, this is a blowtorch.
Where's it at?
It is southeast of Cottersport, Pennsylvania. If you are familiar with where Bradford, Pennsylvania is, it's about an hour east of that. It was also, Cottersport, trivia, was the last residence of Eliot Ness.
Oh.
In June, the Cherry Spring, they host a big star party. I think June 11th is when it's supposed to be this year. It's one of the bigger star parties in this part of the country.
And Sierra Club actually does trips up there too. They take like a group of 10, and you get access for like 4 or 5 days, 4 or 5 nights, I should say. Hiking and stuff around it too. But yeah, the stargazing is the access point.
Cherry Spring is not that large, so if you want to go, especially on the weekend, you'll have to go online and book a reservation, otherwise you'll get turned away.
Well, I guess they gave me a pretty long string here. I'm something of a pacer, so I'll be moving about. Welcome to the Astronomy Club of Akron's annual telescope seminar. My name is John Crilly, and I'm very pleased to be a part of it this year. I'm an attorney in Akron and a longtime hobbyist astronomer. And I'm trying to combine the hobbies a little bit. We shifted things around a bit, which actually benefits us because chronologically, refractors came before reflectors, so now we're doing them in sequence, which is a good thing. The key thing, and Phil mentioned it, is that refractors as a design don't scale up well in aperture. So as people started requiring greater apertures, the design ran out of smoke. Galileo was the first one we know about that wrote about the astronomical use of refractor telescopes. Isaac Newton, is the first person we know about that wrote about reflecting telescopes. So the standard reflector telescope is known as the Newtonian reflector. Am I disengaged here?
You have to hit that button.
Jerry.
You have to X out.
Well, there we go. So I'm going to have to skip a few slides. I noticed that some of these Phil either stole from the same place I stole them, or
Great minds think alike.
reflectors. This is a little bit of a amusing photograph, but it's also illustrative of how reflectors work. Unlike a refractor where you've got a lens up front that gathers the light and sends it back to where the eyepiece is, in a Newtonian reflector, there's a curved mirror. There is no lens. The mirror is at the back. Light comes in, goes down the tube, hits this paraboloid curved reflector, curved mirror, and the light is reflected back forward to where it reaches a focal point, a focal plane, where there's an image to look at. An obvious issue is, well, if you're standing there looking down the tube, your head's in the way. And Newton got around that. Here's just some general pictures of Newtonians that I've owned over the years. I used to be a big fan of Dobsonian Newtonians. So when a newt, the light comes in, goes past the guy's head, hits the curved paraboloid mirror, the light is focused and it goes back forward. But in this case, what Newton did was he put a plane mirror. This mirror does not do anything optically, it is flat. All it does is redirect the light. This light cone that's headed back towards here gets deflected up to an eyepiece here, so the observer's head is not in the way. And this mirror here, we call it the secondary mirror, it's the source of tremendous, am I blocking? I'll try to stay out of the way. It's a source of tremendous conflict because they're refractor guys, and I was a refractor guy for a long time. They like the idea that there's nothing interfering with the view, there's nothing blocking the light, and there's nothing creating diffraction effects as the light passes the edge. The trade-off is you can only build a refractor so big before it starts becoming silly. Percival Lowell proved that. He had what was probably the largest refractor at the time ever made, produced for him. He was an amateur, didn't have much knowledge of science or optics, and he designed or had them design and build a telescope that could never work well. He tried to scale up a refractor to 20 or 30 inches aperture, which can't be done and still perform well. The chromatic aberration was immense. Red came to focus 10 inches or more away from where green came to focus. You'd have to move the eyepiece that far. The chromatic aberration was awful. To get around that, when he wanted to get high detailed views of planets, he had to mask the aperture down to 2 inches, 3 inches. Tiny, tiny aperture. And of course, that created a really high focal ratio. And that high focal ratio was the result of all of his discoveries. He thought he saw canals on Mars. There aren't any. He thought he saw surface detail on Venus. You can't see surface detail on Venus. Everything he's famous for was imaginary and caused by his poor choice of a telescope. So yeah, refractors, it's nice that they don't have an obstruction, but the obstruction buys you quality if you need to get aperture. So what happens is the light passes this edge, there's a little bit of refraction there. The other problem is that mirror has to be mounted somehow. It's normally mounted by what we call a spider. These vanes extend in from the tube and they suspend the mirror in space. Well, now there's a problem. As light passes these edges, you get diffraction effects in the form of spikes. That's why sometimes when you look at an image, it'll have spikes sticking up out of the stars. Those are diffraction spikes caused by that structure. At the back, if you get a chance later, there's quite a long reflector on display, and you'll notice that it does not use a spider. They used to occasionally do it this way. They would put a stem from the focuser assembly and just one arm that would hold the mirror in place. That worked okay for small light mirrors, but as reflectors get bigger, the secondary gets bigger. A 20-inch refractor will have a secondary mirror that's maybe 4 inches, and that's getting to be fairly heavy, so the structure has to be a little tougher. But what's magical about this is light does not bend. There's no refraction taking place. Therefore, there's no scattering of colors. In fact, way down into the infrared where we can't see and way up past ultraviolet where we can't see, everything still focuses at the same point. So, except for the expense of making a parabolic mirror, you can make a reflector pretty cheap. Yeah, let's go ahead. The next step after the Newtonian reflector, the problem with refractors and with Newtonian reflectors is whatever the focal length of the telescope is, of the objective lens, that's how long the tube has to be. If you want a lot of focal length, 2,000 millimeters, 3,000 millimeters, I've shot as high as 3,900 millimeters focal length. That would be 4 meters long. So the Cassegrainian reflectors happened. You still have no refraction taking place, you still have no color error. But what you have is a more complex structure. Now the light comes in, hits your paraboloid mirror, reflects forward, but it's deflected by another curved mirror. This is not just a flat secondary like in a Newtonian. This primary is maybe f2. The secondary is maybe f5. And now the light comes out through a hole in the primary mirror to where the eyepiece sits. But now, because we've got this multiplying factor with the secondary mirror, the tube is only maybe a meter long, but the focal length of the instrument is 2,000 millimeters, 3,000 millimeters in a very compact space. This is why for many, many years, all of your professional observatories used Cassegrainian reflectors. They could have massive aperture and massive focal length, but with a relatively short tube. The instrument might only weigh 400 or 500 pounds, which you can support that. So these were the standard. The best known derivation from this design is the Ritchie-Chrétien. The Hubble Space Telescope, when it was designed, was supposed to be a Ritchie-Chrétien. Ritchie-Chrétien is this same telescope, except this mirror is curved more sharply. It's a hyperboloid. It's not a paraboloid. It goes beyond into hyperboloid space. This is also a hyperboloid mirror. That enables you to make, if you can make it optically faster, it can be f7, f8, and still have acceptable aberrations. This is called the classical Cassegrain. They're normally around f12. Anything faster than f10, you start getting aberrations with this design. The Ritchie-Chrétien fixed that. Of course, the Hubble didn't turn out to be a Ritchie-Chrétien after all. Once they got it launched, they realized that they had made an error in figuring the primary mirror, and it had bad spherical aberration. Fortunately, they were able to take images with it and analyze those images and determine exactly how much spherical aberration there was. They designed an additional optics package that could be inserted into the light path that would correct that. And we actually sent people up. And they opened Hubble up and they inserted this package that it was never supposed to have into it, which was refractive. It was lenses. So it's no longer a pure reflector, but now it gives good images. Hubble, throughout its entire service life, Hubble has been using that add-on package that corrected for the aberrations, and it produced bazillions of wonderful images. There are combination telescopes I'll mention briefly. These are not as important as they once were. It was at one time fairly difficult and expensive to make a good quality parabolic mirror. You can make a spherical mirror pretty easily and inexpensively, but the paraboloid shape was harder to do. And Schmidt came out with the Schmidt corrector, which is a way to, you could use a spherical mirror instead of a paraboloid, and the Schmidt corrector would correct for the spherical aberration. Maksutov came up with his version of a corrector. Again, you could use a spherical primary instead of a hyperboloid or a paraboloid, and it would correct for it. So that you get these derivations. You got the Schmidt Newtonian. Whoops, don't do that. It's a Newtonian, except it's got a spherical primary instead of a paraboloid, which means it has to have a corrector plate on the front. Maxitov Newtonian, same thing. It's a spherical primary mirror and a Maxitov corrector up front. Or you can do it with Cassegrains. Classical Cassegrain would have had a paraboloid in back and a paraboloid inside. A Schmidt Cassegrain has a spherical primary and a spherical secondary inside, and then a corrector up front, a Schmidt corrector. Or you could do it with a Maxitov corrector. Same thing. Those aren't as important anymore because with modern machining, they can produce a parabolic mirror just as fast and just as cheaply as a spherical. So we don't see those derivations. The Schmidt Cassegrain lasts. They're still producing it, they're still popular. And it's because it gives you a lot of focal length in a small package, as we described earlier. And they're light and they're physically short. I've got a Schmidt Cassegrain in my observatory, modified Schmidt Cassegrain. The two instruments in my observatory are a Rowe Ackerman Schmidt astrograph, which I probably won't talk about today, and a modified Schmidt Cassegrain. So they're called catadioptrics. They've got both refractive and reflective elements in them. And basically how they work is light comes in, hits a spherical primary, gets reflected forward, but notice it's going through something here. That's your Schmidt corrector. Light comes in through the Schmidt corrector, hits the primary, reflects up to the 5x secondary and out the back. But because these mirrors are spherical, you would have bad spherical aberration, but the Schmidt corrector takes care of it. Maxitov's the same kind of thing, except the Schmidt corrector is a fourth order curve. It's very complex. It would be very difficult to grind that. They don't grind them. The Schmidt correctors are produced by spending a lot of time and money grinding a metal surface to the exact right curve. Then they take the glass, they heat it, and they place the glass against this curved metal surface in a vacuum that sucks it down against the surface and deforms it until it acquires the shape that the metal surface has, rather than grinding the glass directly. Maxitov wanted to do it more cheaply. He uses a spherical corrector. That's a spherical curve. And you can actually grind that. Because it is a spherical curve, it's much thicker. The Maxitov correctors are quite heavy. The Schmidt Cassegrain, the Schmidt corrector is like a piece of window glass. It's very thin, very light, very easy to shatter. I've only ever broken one. But again, it's either a Schmidt corrector or a Maxitov corrector. You don't see the other derivations. You still see the Schmidts because they're inexpensive. Celestron popularized those back in the 60s. The Schmidt Cassegrain is actually a derivation from the old Schmidt camera, which was a device back forever ago. It had a very fast f2 spherical primary mirror. So it had tremendous spherical aberration, but what they did was, it was only a camera. Inside, where the light was coming back up forward, they had a curved plane, and they would, it was an oops, they would curve the film against that curved surface, so that the film was actually curved and would accept this highly spherically aberrated image and wind up, when you folded it back flat again, the image would be flat. They were used for wide field, very wide field, because they were f2 star imaging. The Rowe Ackerman Schmidt astrograph is really a derivation of that. What they've done is they've added an optics package, refractive, that corrects for all those aberrations without changing the photographic speed. So it's still f2. So I've got an 11-inch Schmidt astrograph that has a focal length of about 600 millimeters. So it's optically very, 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 very fast, which for astronomical use is cool. because astronomical imaging can take some long, long exposures. So we're taking pictures of dim things. Also, it's a very, very wide field. 600 millimeters, that gives you can get a 5-degree field. If you want to shoot something like M31, that's nice. Most imagers have both a long focal length or medium focal length and a short focal length instrument they go back and forth between, because different objects favor one design or the other. I have them both mounted side by side on a common mount, so I can just go back and forth. We're going to skip mounting, except to say that there are Dobsonian mounts, which looks like a medieval cannon. If you go in the Caribbean, you go on the islands, they all have these cannons and forts to repel invaders. That's the kind of mount they have. They're gimbal mount. It swings around and up and down. John Dobson, of course, popularized that style of mount, and that's why it's called the Dobsonian mount today. Dobson was he was a monk, a spiritual kind of guy. He had the vision that if everybody on the planet had a telescope or could look through a telescope and see how vast the universe is, the differences between people would start to seem pretty insignificant, and we would all get along. Typical California.
Yep, good concept.
He was wrong, but he had this notion that if you could make a telescope so easy to build and so inexpensive to build that everybody could build one, everybody would. And he popularized this mount, which was the cheapest and easiest possible telescope mount, and yet very effective. You know, that's a 20-inch instrument there on a Dobsonian mount. It's a good mount, very cheap to make, very, very effective. And they wanted to use discarded ship porthole glasses for mirrors because they were round. Everybody could grind their own mirror, and everybody can. Nobody does, very few. So he popularized the idea of making a telescope very, very cheaply and very, very easily. And, well, we all like telescopes. We all like astronomy. But you know what? We're nerds. Nobody else does. So it didn't become a popular revolution, and it didn't change society forever. But he's remembered. His mounts still produced today, still used heavily today. They just didn't change the world quite the way he thought they would. For imaging, we have to have equatorial mounts. Well, I say that the professionals do not use equatorial mounts, but all the amateur imagers do. The reason for that is if you track in altitude and azimuth, which you can do, and which every professional observatory does, as you go across the sky, the field rotates. So you get smeared images. You have to have a field derotator that rotates your camera at exactly the right rate to cancel out that field rotation, which varies depending on where you are in the sky. So it's not just a plug in a motor and run kind of thing like the mount can be. It takes a lot of control to know exactly how much to derotate at any given portion of the sky. The pros can afford this. You know, they got their $10,000 telescope on a $20,000 mount. They can afford a couple grand for a nice derotator. Amateurs don't do that. Almost never. There's only ever been one effective field derotator offered to the amateur market, and nobody bought it. Meade, on the other hand, produced one that sold for $200, but they didn't work. So that never solved any problems. I have this picture just because this is a Vixen Great Polaris mount. The first really popular, really high performance, really almost affordable equatorial mount. They were produced in Japan. And what's interesting about it is that it produced a whole cottage industry, entire companies, entire industries were formed for the purpose of cloning this mount, knocking this mount off, and making cheap Chinese copies of it. And Meade got famous doing it, and Celestron got famous doing it, and whoever owns Cinta got famous doing it. And I forget the company that made them for Meade, they got famous doing it. Just shameful copies. This is why we have to have rotation, not derotation, but equatorial tracking. If you just go altitude, if you just use altitude and azimuth, your stars are not good. And if you use equatorial tracking, your stars are good. That's easy. Here we go. This one, I'm going to answer a question that was asked earlier. Two different ways. Because the question is, really, how big a telescope do I need? What does aperture buy me? The conventional wisdom, everybody always says, hey, more aperture, more light gathering, you'll see dimmer objects. To some extent that's true, although if you're in light polluted skies, the additional aperture also brings in more light pollution. Nonetheless, aperture buys you light gathering ability. But it sometimes is more important that it buys you resolution. The maximum possible resolution, if everything else is perfect, is so many arc seconds. Increased aperture gets you higher theoretical possible resolution, and we can see it. Here's what a couple of craters on the moon look like in a 3.5-inch telescope with everything perfect. That's not atmospheric disruption, that's not eyepiece aberrations, that's what the maximum resolution you can get is. You look at the same area of the moon with a 14-inch telescope, look at the higher resolution. That's real. You talk about the Dawes limit, you talk about the Rayleigh limit, where they tried to calculate the maximum possible resolution for a given aperture. This is it in real time. This is the actual difference. And I have another demonstration of the same thing. Let's look at a deep sky object. Let's look at M13. Very pretty globular cluster. We love looking at it. When we go to outreach events, we always show it to people because it's pretty. People are curious about it. And it's bright. You can see it in a small telescope. But how well can you see it? This is the kind of resolution you can hope for. And these are all taken at the same magnification, 150x. 2.5-inch telescope, yeah, it's a glob. You can tell it's a glob. As your aperture increases, you start seeing some resolution. And this is my demonstration of why an 8-inch telescope is the perfect telescope. And again, you go on up to 14 inches, look at the resolution. This is my demonstration for why when people ask what your first telescope should be, I tell them the opposite of what everybody else tells them. I tell them get an 8-inch Dob. An 8-inch Newtonian can see a lot. It has enough light gathering ability, you can see dim objects. It has enough resolution, you can appreciate seeing objects. It's a nice round number. Conventional wisdom is, well, the old conventional wisdom, which I do buy, is binoculars. Get binoculars first, learn the sky, then talk about telescopes later. But if you're talking about your first telescope, most people are going to recommend a short refractor. 3-inch aperture, maybe 4, 600 millimeters focal length, maybe 800. Something that's manageable, it's physically short, it's not going to strain your mount very much. But I like an 8-inch Dob, and this is why. I think that's everything I have that's appropriate for what we're doing. Oh, one more, magnification. How much magnification do I need? Okay, here's what magnification buys you. Saturn at 50x. It's about the size of a pencil eraser in your eye. You see the rings. Right now you can't. Saturn is inconveniently placed right now. The rings are edge on to us and they just disappear. There's about a 15-year cycle. 15 years? Anybody correct me on that?
Average every 15 years.
Okay, 15-year cycle. Because effectively it rocks as the alignment between us and it, everything changes. So every 15 years it goes edge on and the damn rings disappear. Which really hurts us, because at outreach events, what do we show people? We show people M13. And if it's available, we show them Saturn, because they can't believe that. I can see the rings. Yeah, you can. They look great. Except not right now. But these were taken at a more opportune time. And at 100x, we're starting to see some detail. We're seeing the shadow a little bit. We're seeing the gap. When we get up to 400x, look at that. We're seeing the division. We're seeing the shadow, we're seeing the cloud bands. Here's the problem. 400x, it takes a certain amount of aperture to be able to resolve at 400x. It's probably 10 or 12 inches to really be able to use 400x without aberrations. But we're in Ohio, and well, we're on Earth. Most nights, if you go out and try, you'll find that our skies top out right around 200x. There are magical nights. You can have an eyepiece that'll give you 400 and keep it in reserve for those magical nights when it works. But most nights that eyepiece is going to be useless to you. You're going to be topped out here, which is a nice view. We just can't expect that kind of view with any regularity with the kind of skies that we've got. We're unfortunate in that way. Then again, we do get to breathe the air, so the atmosphere is of some benefit to us.
Very good.
But it's also a problem.
Question.
It's time for questions. Go ahead.
Ron, what power do we usually see something at the observatory?
Ron.
100. Most of the time 100, we use the 40 millimeter super wide mead. Sometimes we'll put the 31 millimeter Nagler in and that'll give us 130. But most of the time you can't go above that. You're amplifying all the distortion in the atmosphere, so that turns out to be.
That's a Smith Castle ring.
Yes.
Anything else? I came all the way here.
Yeah, I have a comment for Ron. Ron knows I own a smart telescope. More people are buying them, and I'm just asking Ron if that might be talked about next year, maybe a smart telescope, my C-star.
Yes.
So I'm asking if it might be included next year, something like that.
You mean at a star party?
No.
At the presentation.
Presentation.
I would support that. I can tell you that when I'm out talking about astronomy, I talk about imaging quite a bit. And in my imaging presentations, I get questions about that.
Yeah, some.
People bring it up, and I have to say that although I've been doing it the other way for 25 years, I have zero experience with that. I would be interested in learning more about it too.
Yeah, some people hate them, the old guard hate them, but.
Oh, I'm sure I will hate it, but I don't know yet.
But the newer people seem to like it.
Oh yeah, I get questions about it all the time. I just don't have answers.
Yeah.
So thanks for bringing that up. Ron, I would support that.
Yeah, we have two, because, I'm sorry, I forgot your name.
Me?
Yes.
Jim.
Jim, yeah, Jim has one too.
I actually
Oh,
saw
Ron.
it today.
Okay, well,
Yeah,
you're gonna have to recruit one of them, cause I don't know anything about it. But yeah, I would like that.
Yep, door 3.
I am on a C-star.
Yeah.
Well,
I
maybe
wanted to
two
see
seats.
what, I wanted to look into those ones. I just-
Put something together, we can use it. Anything else that I can answer? Yeah.
You said that spherical mirrors have gotten easier to manufacture. The one at our observatory is spherical, right?
Yes.
If you're buying that today, would a parabolic be competitive, or is still not?
You might be thinking backwards, that the parabolic was the one that was harder to make,
Right.
It's now easier.
which is now easier, right?
John said it's easier.
So now you could make a classical Cassegrain instead of a Schmidt Cassegrain and get rid of that corrector plate.
But Meter or Celestron don't make that, but you can get like a plane wave one that has a parabolic
Yep.
mirror that, you know. would-
Well, actually, it's worse, the plane wave actually has a spherical mirror. That's how far we've gone. $20,000 instrument's got a spherical
yours?
primary in it.
It's mine, yeah.
Why? Well, because it's what's called a corrected CDK, a corrected Dahl-Kirkham. I mentioned derivations from the classical cast, and I mentioned you can push it harder and go to a Ritchie-Chrétien and speed it up. You can also slow it down and go less than parabolic. And I forget the term for that, but it's not quite a paraboloid. And it's like a Takahashi Mulan or any Dahl-Kirkham. And they have to be very slow, F13, F15 in order to work. So what PlaneWave does is they've got a Dahl-Kirkham and they've added an optics package, just like we did to Hubble. There's an internal optics package that speeds it up and corrects the aberrations. So a corrected Dahl-Kirkham can be like F8. And it is relatively short too. A corrected Dahl-Kirkham would be about the same size as our Schmidt. But it would cost about 15 grand more. But it would be a better imaging instrument. The Schmidt Cassegrain is a swell visual instrument, but it falls apart a little bit for imaging. That's why I've got a modified Schmidt Cassegrain. Mine's F8, and it's more imaging optimized than a conventional F10 Schmidt. So, yeah, I don't know who's using a paraboloid. Now that they're cheap and easy to make, nobody's using them. Even the Ritchie-Chrétien, which is hyperboloid, which was harder to make, those have really fallen apart now in the market. The people that were making those aren't making them anymore. The big kids are all using corrected Dahl-Kirkhams. And they're paying big bucks for them, and they're professional, wonderful instruments. So yeah, they're paraboloid. Now that it's easy to make it, we're not using them anymore, except for Newtonians. So we still use paraboloids for newts. Well, with that, hey, thanks for coming.
Thank you.
Thanks for sitting through it.